Hello, my name is Joe Fioresi from the University of Central Florida. Today, I'll be presenting my work titled TeD-SPAD, Temporal Distinctiveness for Self-Supervised Privacy Preservation for Video Anomaly Detection. In this task, we're given long continuous videos along with video level labels, so weak supervision, and our objective is to find when anomalies occur. We do this by outputting frame level anomaly scores like the ones in this graph. Our motivation here is that this can reduce the time and resources humans spend monitoring videos, and that the automation can lead to accurate, timely responses from the appropriate parties. To process these videos, we may need to send them away from the edge camera to some form of computation cloud. Doing so risks leaking these private attributes seen in the frame on the left, such as hair color, perceived gender, or the clothes they're wearing. This information might also be used in the decision-making process, which can lead to biases related to these attributes. To prevent this all, we propose to anonymize anomaly detection. In this anonymized frame, we can still make out the action that may be occurring, but we are unable to see their private attributes. This graph shows the reduced privacy leakage that we get from our method, reducing from around 62% privacy attribute prediction to around 42%. Now we look at the TeD-SPAD training algorithm. First, we start with some notation and model initialization. Then we move on to the anonymization training. Start with an action recognition dataset, then pass each frame through a unit anonymizer, which is trained in such a way that decreases the loss on the utility action recognition task and increases the loss on the budget privacy task. Our utility loss is simply cross entropy plus a weighted distinctiveness loss. And this distinctiveness loss is motivated by the fact that weakly supervised video anomaly detection models, like MGFN in this work, utilize the variation of features to help localize anomalies. So essentially, we want clips within the same video at different timestamps to have distinct features. We accomplish this by this triplet loss, where we encourage similarity between features of different augmentations of the same clips, and we repel these features from the representation of a clip at a different timestamp T prime. After this training, we take our anomaly detection dataset, pass it through the trained anonymizer, and then we get our anonymized videos, which we pass through our trained feature extractor until we get our anonymized feature set. We take these anonymized features, then pass them through any weakly supervised anomaly detection algorithm, and then we get our output anomaly scores for evaluation. Once we have the trained anonymizer, we can visualize it. If we look at this raw video, we can see the subject's private attributes, but then in the anonymized version, we still see the action they're performing, but none of their private attributes. We see the same thing in this video, and then the following two examples. These are frames sampled from a long continuous video along with the anonymized versions, and we see consistency in this anonymization. And when we look at the frame level anomaly score plot, we see that the anonymized predictions closely follow the raw video predictions. In this example, we see the same phenomenon as the previous. In these trade-off plots, we compare results to existing privacy preservation techniques on 3 weakly supervised datasets: UCF crime, Shanghai tech, and XD violence. So we see in this first plot that we want to be in the upper left because it shows high anomaly detection AUC performance and low private attribute prediction performance. And across all 3 benchmarks, ours consistently achieves the best trade-off. Because anomaly detection models directly take action recognition features in as input, we first needed to see if these features did leak privacy. We find that they do, at almost the same rate as the raw frames themselves. However, when we anonymize the i3D model, we see reduced privacy leakage. In this ablation, we wanted to test using different utility losses during the anonymization process. We take cross entropy as our baseline, and then we add our temporally distinct triplet loss and achieve our best performance. Yet when we try an invariance loss, which is a counter objective to distinctiveness, so in this we want all clips within the same video to have the same representation, we still get improved privacy preservation, but we get decreased utility costs because this is not well aligned with the anomaly detection task. This ablation tests the effectiveness of different ways to achieve temporal distinctiveness. So we start with a local temporal contrastive loss, which achieves competitive performance to our triplet loss, but the triplet loss is much more computationally efficient. It's important to note here that both distinctiveness losses do improve performance. In conclusion, we presented TeD-SPAD, a framework for anonymized video anomaly detection. We showed that there was a privacy leakage issue in video anomaly detection features, and then we showed a proxy anonymization training with a temporally distinct triplet loss to help fix this. This method outperformed prior privacy preservation baselines on video anomaly detection. So thank you. Come visit our project page.